So in addition to a neutralization reaction, the other types of reactions we can have are ones in which we have, so let's just review first. I guess we should just remember a strong acid, strong base reaction. Strong acid, strong base. And this is a neutralization reaction, so we can use strong acid, nitric acid, and then we can have, in this case, if we, okay, so let's do this. If I did NaOH, aqueous, this is a strong acid, strong base. Single arrow, we make our H2O plus NaNO3, aqueous and liquid. Okay, so this would be a strong acid, strong base. This is a neutralization reaction. Okay, well, let's just change the base. So let's do HNO3, so still a strong acid. And let's just react it with a weak base, which is water. So water, so if I write this out, this is our strong acid, still strong acid. Now this is our weak base. When I say weak base, it is the weakest base, very weak, and I'll show you that in a sec. And in this particular case, the arrow will still be one direction. What will happen is that this acid is so strong that it will dissociate, and it will dissociate completely in water. So basically, the reaction I've done is basically the definition of a strong acid in that it dissolves to form H3O plus aqueous plus NO3 minus, where again, this is the conjugate acid and the conjugate base. Okay, so acid becomes base, conjugate base, base becomes conjugate acid. Okay, so this basically is the equivalent to, we'll do it in gray. This is equivalent to the HA plus H2O. Comes to form H3O plus A minus. So this is what we've already talked about. This is kind of defining a strong acid, or we could do the same thing with a weak base. Now, so when we want to predict this, we would predict based on the strong acid that we would predict that the products would be favored. But what if I took something like a weak acid, so CH, let's do something else. Let's do put that back on. Let's say we do NH3 aqueous plus water. Okay, now if we label these, this is a weak base. It's not one of the strong bases we remember, weak base. And this is would act as a weak acid. Now my question is, well, what happens if I add ammonia, NH3, to water? Do I form? So what could form? Well, if NH3 is a base, the first thing you want to do is you want to say, well, what will happen is, well, an acid will act like an acid, and it will donate a proton to NH3, the base. NH4 plus would be created, and we'd be left with OH minus. Okay? And again, this is liquid, this is aqueous, and this is aqueous. Okay? Now my question is, and I'm actually going to erase this arrow, and I'm going to replace it. Because we have 2 weeks, we are going to have this equilibrium arrow. Now my question is, are we going to favor staying as reactants, or are we going to favor products? Now a way to help us with that is a chart we have right here. So this chart is showing you acid strength on the left and base strength on the right. And so I'm going to highlight a couple things here. We're going to highlight that we have 3 strong acids, and we have um, 2 strong bases. Now these aren't as useful to the ones that we've talked about in class. But what I want to point out here is that we have a whole bunch of conjugate pairs that go across. So, for example, HClO3 is the strongest weak acid in this table. Acid strength is increasing in this direction, going up, but it also shows you that the strongest weak acid is actually the conjugate base. So this is the conjugate base, ClO3 minus. It is actually one of the weakest bases. So remember that a conjugate acid-base pair, the stronger the acid, the weaker the base. And that's why for strong acids, so for example HCl, the conjugate base is Cl minus. And Cl minus is effectively has no base strength. If you were to put Cl minus in the solution, it would not pick up any protons from anything or anyone. So NO3 minus is the same way. It will just float around and never act like a base, never go to form HNO3 again. And so that's because the definition is a strong acid dissociates completely, and that's because it's highly reactive with when we put it into water. So we're going to use this chart to help us predict what is the most likely thing to occur, and it's really simple. So the first thing that we do in this problem is we predicted what would be formed, and so you say, okay, well, you're a base. That means you're going to take a proton here. You're an acid, so you're going to lose one. That's how we get NH4 plus and OH minus. And then what I want you to do is I want you to compare. So we're going to compare. Let's compare bases. So here's our base. And if I finish labeling these, this is our conjugate acid, and this is our conjugate base. And so I'm going to compare the two bases. And I'm going to say which base is stronger. So I'm going to compare this base versus this base. And if I look on our table, so NH3 should be on the base. They're both on base side. So here's NH3, and then the other one is OH minus. OH minus is down here. So this is the strongest is here. So OH minus wins. It's stronger. And what that means is that the stronger OH minus will want to react with NH4 plus and go back. Now, we could also check the acid, and just to show, if we check, let's do that in a different color. So let's say we check the acid, 2 acids here, and I'm going to compare water and NH4 plus. So on the acid side, the left side, NH4 plus is here. It's pretty low down, but when you compare it to water, it is even lower. So this is the stronger acid. Now you'll notice that see how they're across from one another. So because OH minus was a stronger base, its conjugate acid is weaker, and just because NH3 had was a weaker base, its conjugate acid was stronger, and that will always be the case. And so when you find the strongers will always be on the same side of these types of problems, and so the reaction will always move in a direction away from the stronger. And so if we want to predict if these reactions will occur, then you will say that the reaction, so we can say we have reactants and we have products. And if we're trying to compare the two, we would say that the reaction would favor going in the reverse direction. Sometimes we can just go R and P, and we can go like this. Or you can say that the formation of reactants is favored. Okay, so there's 3 different ways to write this, and so this is what we're going to do. We're going to predict are either reactants or products favored. So let's do another example using another acid and base pair. So we'll do that. And so let's have, let's do CH3COOH plus NH3. And so what I want you to do is I want you to predict, are we going to stay as reactants or are we going to favor the formation of products? So the thing we'll do is we first have to say what's the acid, what's the base. I remember that this is a base, which means that acetic acid has to be an acid. And so if you make a base act like a base, it's going to make NH4+. It's going to take a proton, and we're going to take the acid. It's going to donate a proton, so it'll be minus a hydrogen, and it'll be a hydrogen on the end, so that's there. Okay, and so if we label the rest of these, we have NH4+ is going to be our conjugate acid. I'm just going to use the C for conjugate, and our CH3COO-, our acetate, is going to be our conjugate base. Okay, and if we have these, we're going to take the, we're going to go look at our little chart. So I'm first going to compare the acids. So I'm going to take our acids. I'm going to say, okay, here's my acid. And I'm going to say, which is stronger, CH3O, acetic acid or ammonium. So I go on here and I say, well, here's ammonium. Now, where is acetic acid? It's right here. And so acetic acid is more towards the top, so acetic acid is stronger. So this is the stronger weak acid. This is the weaker weak acid. And if we look at our base, we'll go and do the base. Same comparison. We'll do in red. So we're going to compare the two bases. So NH3. So it's easy to find these because they're just on the opposite. So NH3 and acetate. And you'll see the same thing, that the NH3 is farther down, so it is stronger. And so we have the strongers on the same side. That'll always be the case. It has to do with this inverse relationship of strength between acid and base pairs, and that this will be the weaker of the two bases. And so we would show that the reaction always moves away from the stronger. It moves in this direction. So we could say that reactants are going to favor to go to products, or we can say the formation of products is favored. Okay, so those are the two things you can do. So again, just to review, what we're going to do on these is you're going to first define what's the acid, what's the base on the product side. Next, you're going to make the acid act like an acid, make the base act like a base to get your conjugate acid and conjugate base written down. You'll then compare either acid or base. You can do either one. Using this chart here, the strongers will always be on the same side, and then you will say what side the stronger is on. The reaction always moves away from the side where the stronger acid and stronger base are. So you can have the arrow points away from the stronger, the arrow points to the weaker, however you want to remember it. And then you would simply state something like the formation of products is favored, or have an R with an arrow going to P.